Now we will see if we can make some typical magnitude calculations using these statistical arguments. More specifically, I will concentrate on some of the things that come out of kinetic theory of ideal gases. The first task is to determine the pressure of an ideal gas. So if you have an ideal gas inside a rectangular container like this, these gas molecules on average will exert a pressure on the walls of the container, and one way to measure this pressure is using a manometer. So what is pressure? It's force per unit area. So we would like to find out what this pressure, average pressure exerted by the gas molecules is. So let's first note that we have a gas in a container. In this case, it's a rectangular container, exerts a pressure. We usually show pressure with P. And what is pressure? Pressure is the force per unit area. It is force per unit area, and this area is the area that's perpendicular to the force. This pressure is exerted on the walls of the container. And the way we measure this pressure is using the manometer. And if you look at this is basically a tube that is filled with mercury, and on one side the mercury level is here, on the other side the mercury level is here, and the top of the tube is basically under vacuum, so there is no additional pressure coming from the top of the mercury. If the pressure of the gas is too high, what will happen? This mercury column will rise on the right hand side, and if it is too low, then it's going to be lower, so that we need to have at equilibrium zero force, zero net force on the mercury inside the manometer. So I'm looking at the force per unit area in the capillary tube. What is the pressure of the gas, or how can I determine the pressure of the gas? Well, we need to have the same pressure on this point and on this point, so that we're going to have equilibrium, so there will be no motion of the mercury in the capillary tube needed. So how do I measure the pressure of the gas? The pressure of the gas is going to be equal to the pressure on the right hand side. Well, so I have this mercury in the column with height h, so there is a mass of that mercury multiplied by gravitational constant g, it's the weight of the mercury, divided by the perpendicular area A. So what is this perpendicular area A now? It's going to be the area of this column. So it's the cross-sectional area of this column. So I'm going to have the weight divided by area giving me the pressure due to the mercury, and it must be equal to the pressure due to the gas. How do I find the mass of the mercury? It's the density of the mercury multiplied by its volume times G divided by A. And what is the volume of the mercury in this column with height h? it's going to be its area multiplied by h, because it's a cylindrical region, multiplied by g divided by a. So a's will cancel. So I will find that the pressure of the gas that I will read in the manometer will be density of mercury, gravitational acceleration times h. So this is how I measure the pressure of the gas using what is called a manometer. So this is the mercury manometer that determines the pressure of the gas. And now what we would like to do is to try to calculate using molecular quantities what the pressure should be. So can we calculate the average pressure exerted by the gas, that's using molecular quantities? The answer to this question is yes, using kinetic theory. Now, before starting this calculation, I would like to remind you about our assumptions of an ideal gas. So remember that our ideal gas is dilute. It's a low pressure, low density gas. The number per volume number density is low. It's a non-interacting free gas. The molecules do not have any interaction force between them. The average distance between the molecules is much greater than the molecule dimensions. They are point-like particles, so their dimensions are negligible. The average distance between the molecules is much greater than the de Broglie wavelength, so that quantum mechanical effects are negligible, which means classical mechanics applies, so Newton's laws of motion applies. And we will have rare elastic collisions between molecules and between molecules and the walls of the container. And these elastic collisions will have, of course, kinetic energy and momentum conservation. And there will be linear trajectories between collisions, because between collisions they don't feel any forces from other molecules. They are free to move. So let's start this calculation for the gas that is trapped inside a rectangular container. So I have a rectangular container that has capital N molecules. Inside this container, and molecule mass, one molecule has mass m, and the number of the molecules inside the container divided by its volume, container volume is V, so that I have the number density capital N divided by V, that is number of molecules per volume. It's the number density. Okay. And this system is in equilibrium. There will be an average speed of each molecule. So this V bar I call average speed of a molecule. And remember from our previous arguments, we have a most random distribution of energy. So if this is an isolated box, this is isolated, we have total energy divided by capital N is the energy, average energy per molecule, And if it's a monatomic gas, it will only have kinetic energy contribution. So the average speed of a molecule is basically determined from these arguments. Okay, now, so considering the three dimensions x, y, and z, and I have a completely random distribution of molecules, basically I have three independent degrees of freedom, x, y, and z. So out of these capital N molecules, I basically statistically can say that 1/3 of them will be moving along x-axis, 1/3 along y-axis, 1/3 along z-axis, because I have completely random motion of the molecules. So on average, I can say that 1/3 of the molecules per unit volume will be moving along either x or y or z axis. And the reason I can say this is because this is a random motion, so statistically on average I will find that each axis has 1/3 of the molecules moving on them. So I have 1/3 of the molecules moving along x-axis. Now I would like to find out how many of these molecules are going to go in positive x-axis and hit the right hand side of the container walls. But the same statistical argument, I will say there is no preference between positive x and negative x. So if I have 1/3 of the molecules moving along x-axis, half of them will be moving in positive x direction, half of them in negative x direction. So I can say that on average, again, 1/6 of the number per volume of the molecules move along or let's say move in positive x direction. Okay, so let's say that I'm looking at a time interval t. So I'm going to consider a time interval t, which is much less than the average time that is needed to have two molecules collide with each other. So this t bar collision is average time between molecule collisions. And remember, we were saying that these collisions are rare, so this time could be quite large. And so I'm picking some time interval that's much less than the time that's needed for molecule to molecule collisions. What does that do for me? Well, basically this is to guarantee that in this time interval in time t, I will have no molecule collisions. All right. So if you look at a volume in this container that is right next to the right side wall, basically I'm looking at this volume here. I have the area of the wall on one side, and so there is this area here, area A, and then on the other side of this rectangular box I have V bar times T. So basically that is the length scale over which the molecules will come and hit the wall. Okay, so basically what I'm trying to get at is how many molecules are going to hit the wall in the time interval t. So if a molecule is within a distance v bar times t from the wall, what will happen? It will collide with the wall because it cannot collide with other molecules. The time interval is too small for that. That's because of this assumption. So it will collide with the wall. How many molecules collide with the wall in time interval t? Okay, so I'm trying to calculate the number of molecules on average colliding with the wall in time interval t. Well, there were 1/6 of the molecules per unit volume moving in the positive x direction, and the number will be the number density 1/6 times nv multiplied by the volume. What is the volume? It is area b bar t. So this is the volume of the rectangular box that is right next to the wall. So this will be the number of molecules colliding with the wall in time interval t. Okay, now I want to know average number of molecules striking the wall per unit area per unit time. So what is the average number of molecules striking the wall per unit area per unit time? Now I have found out that I have 1/6 and v bar a t. Let me write it this way. 1/6 and v, the number of molecules on average moving in positive x direction multiplied by volume, number density multiplied by volume, gives me the number. Now I have this number. I want to know per area per unit time. So this is going to get rid of this area and time, and I will have an answer 1/6 number density times the average speed of the molecules. So with these statistical arguments, I get at the molecular flux density, which is by definition the number per area per time. This is equal to 1/6 number density multiplied by average speed of the molecules. This is one way of approximating the molecular flux density using these statistical arguments. It's actually not quite right. So let me open a remark here. Remark. Later on, we will see this is not quite right. We have something called Maxwell velocity distribution. Maxwell velocity distribution, which we will talk about later on, gives us the proper molecular flux density to be 1/4 and v bar. Okay, so there is a problem with this number here using purely statistical arguments, purely random distribution of velocities, but there is actually some preference. So there's a Maxwell velocity distribution which one should take into account when calculating the molecular flux. Okay, so for now we will continue with this crude statistical argument giving us the molecular flux density 1/6 nV bar. Okay, now consider that you have a molecule that has a mass m, and that's coming and hitting this wall, so it has average speed v, and because this is an elastic collision, so let me remind you, it's an elastic collision. In elastic collisions we have the kinetic energy is conserved, so after the collision it's going to come out this way. So this is before, this is after the collision. And kinetic energy did not change. Delta K is 0. What is the change in the momentum of this molecule? Well, if I write this as a vector, so remember that this is my positive x direction. So the final momentum minus initial momentum, it is minus mv bar I hat minus mv bar I hat. So because plus mv bar I hat was the initial momentum. So the change in momentum of the molecule is minus 2 mv bar I hat. Because you have a momentum conservation for the system of the molecule plus the wall, what is the change in momentum of the wall? It's going to be minus the change in momentum of the molecule. And so this will be 2 mv bar I hat. That's the change in momentum of the wall. So we have in classical mechanics the famous impulse momentum theorem. And what does this theorem say? The impulse that you apply to a particle, or in the wall in this case, is given by integral of the force that you apply in the time interval dt, and that is equal to the change in linear momentum delta p. So this implies that you're going to have in the time interval t, I'm assuming that we have the same force being applied. So if this is a constant force, if f is a constant, then we're going to have the impulse equal to f times t, the time interval in which we apply this force. Okay, so this impulse is going to be acting on the wall. So the impulse on the wall is the force exerted by one molecule multiplied by the time of the collision with the wall. So this collision is occurring in the time interval t, and that is going to be equal to the change in linear momentum of the wall. So I will find that F, force exerted by one molecule, then F is going to be equal to 2 mv bar divided by t. This is the force exerted by one molecule. What is the total force exerted by all the molecules. So let's call this force exerted by the ith molecule. So let's say this is Fi, Fi, Fi. And actually there is an average force exerted by this molecule. So let's call this Fi bar. So Fi bar is the average force exerted by one molecule, the ith molecule, in the time interval t. Okay. Now what is the total force? What is the total average force? It will be the sum of all the forces exerted by the molecules, where I will go from 1 to the number of molecules exerting this force. Okay, total number of molecules exerting this force. So this is going to be, because I'm assuming I have the same average force exerted by each molecule, it's going to be equal to the force due to one molecule, 2 mv bar divided by T, multiplied by the number of molecules. What is the number of molecules? It is 1 over 6 NV A V bar T. So remember, this is the number of molecules moving in the positive x direction. So this is going to give me, the T's cancel, 1/3 NV area A m V bar square. Now remember what we defined as pressure. Pressure is the force per unit area. So this is the definition of pressure. So we want to know the average pressure exerted by these gas molecules. Well, then the average pressure exerted by the gas molecules will be this quantity divided by the area. So this is going to be total force so it will be this quantity divided by the area. It will be the total force divided by the area is the average pressure. It will be 1/3 number density m v bar squared. Now this mv bar squared basically should remind us of the kinetic energy of these molecules, so we can take it one step further. What is the average kinetic energy per molecule? So we have 1/2 m v square average. So we can basically make an assumption that assume statistically v square bar is not very different from v bar squared, the average speed squared. So I can estimate the average kinetic energy to be 1/2 m v bar squared instead of v square bar. And with this, the average pressure that I find here is 1/3 NV 1/2 m v bar squared times 2. So in order to get the mv bar squared here. So this is basically going to tell me the average pressure here is 2/3 NV average kinetic energy per molecule. All right. So basically we find that the pressure is a measure of average kinetic energy per molecule. So if you increase, so if you think about this, does this make sense? If you increase the number per unit volume, the average pressure that you observe will increase. If you increase the average kinetic energy per molecule, the pressure will increase. And remember from our previous discussion on temperature, what did we find? The temperature is related to the average energy per atom or molecule. So average kinetic energy per molecule will be a measure of the temperature as well. So this is going to imply as temperature increases, average pressure exerted by the gas molecules will increase. So these all make a qualitative sense. Okay, so an important result we found is that a measurement of the average pressure exerted by the gas molecules provides information on average kinetic energy per molecule. So it's epsilon k bar. Okay, so let's repeat what we said. We started out by looking at what pressure means. If you have a gas inside a container, there will be force applied by the gas molecules hitting the walls of the container. So on average you will have a pressure inside this container, which can be probed using a mercury manometer. And a mercury manometer consists of a capillary tube that has mercury inside it, and one side is under vacuum so that there is no additional force on that side. The pressure on one side is balanced by the pressure on the other side due to the weight of the mercury per unit area of the capillary tube. And we find that the pressure of the gas should be equal to the density of mercury, gravitational acceleration multiplied by h, the height of the mercury column, the excess height of the mercury column. And then we asked, can we calculate this average pressure using some molecular quantities, using our statistical arguments? The answer is yes, using kinetic theory. And kinetic theory uses the assumptions of the ideal gas. We have a dilute, free gas which consists of point-like particles. Classical mechanics applies and all collisions are elastic. And then we looked at the gas inside a rectangular container with capital N molecules. The total volume of the container is V, so capital N divided by V is the number density. And since this is at equilibrium, so we have assumed that this is at equilibrium, we have the most random distribution of energy. There will be a well-defined average speed of a molecule. And on average, 1/3 of the molecules will be moving along x, y, and z axes because it's a random motion. And on average, statistically, we will say half of that 1/3 will move in the positive x direction. Now, if I take a time interval t, which is much less than the collision time, average time needed for molecule-to-molecule collisions, I will make sure that if I have a volume V bar T times area A of the wall, I will have, so that's the area in this region here, I will have no collisions between molecules but only collisions with the wall. Okay, so that's because the time interval I have picked up is too short. Now, if a molecule is within a distance V bar T from the wall, it will collide with the wall, not with other molecules. How many molecules will be colliding with the wall? The number density NV multiplied by 1/6, which I found statistically the number of molecules moving in positive x direction, multiplied by the volume of this region. What is the volume of this region? The volume of this region is A B bar T. That's the volume of this region. And I multiplied with the volume, I get the number. Now it's number per area per time, it becomes molecular flux density, 1/6 NV bar. And then I had a remark here, actually There is the Maxwell velocity distribution, which will tell us it's not quite right. It should be 1 over 4 mv bar. But anyway, we're just trying to get the sense of the dependence on physical quantities here. So we will continue with the statistical argument of a completely random distribution of velocities. So you have 1 over 6 mv bar. If a molecule comes and hits the wall with a momentum, initial momentum P initial is mv bar I hat, P final is minus mv bar I hat. It's an elastic collision. There will be no change in the total momentum. Therefore, the change in momentum of the wall should be plus 2 mv bar I hat. And the change in momentum of the molecules minus 2 mv bar I hat, so that I have no total change in momentum. Delta P total must be 0. That's because it's elastic collision. Also, the kinetic energy of the molecule should not change, therefore it should reflect with the same average speed v bar. Okay, so what changes the momentum of the wall? 2 mv bar I hat. The impulse momentum theorem tells me there is a force exerted by the gas molecules that caused this change in linear momentum in the time interval t. If that force per molecule is the average quantity, it's a constant over the time interval t, then the impulse will be just force multiplied by the time interval t. So I will find that average force per molecule is 2 mv bar divided by t. What is the total force? Well, I have to multiply the average force per molecule with the number of molecules hitting the wall in that time interval. I find that this is 1/3 mva mv bar squared, because pressure, average pressure is average force, total average force per area. I have to divide it by the area of the wall on which the molecules are impinging upon, so it's going to be 1/3 mv bar squared. The average kinetic energy per molecule is also approximately 1 over 2 mv bar squared, so just multiplying the average pressure with 2 and 1 over 2, I obtain the dependence on average kinetic energy. Average pressure is 2/3 number density times average kinetic energy per molecule. And this formula tells me that if you increase the density of the molecules, if you increase the number per volume, the average pressure that they exert on the wall will increase. If you increase the average kinetic energy of the molecules, or if you basically, that's the same thing as saying if you increase the temperature of the gas, the average pressure they will be exerting on the walls of the container will increase. So we're going to use this result and we will try to quantify so the pressure from an ideal gas, average kinetic energy of an ideal gas, etc. Using this theory in the next